Hi everybody and welcome back to this new DIY video. I'm about to show you what's in this black box. Ladies and gentlemen, I present you the Cam87 Astrogating edition. I'm gonna tell you the story of this camera and how I designed it. The body of this camera is made by a gas-tight aluminum box. On this you can find a 3D printed box. We're gonna see later why. You can see a fan and a heat sink because below there is a Peltier module because this camera is a cold camera. And you're gonna see now what there is behind this cap. This is an APS-C color CCD sensor with 3000 by 2000 resolution. This is the ICX453AQ by Sony. Let's go now to take a look at the designing choices and the construction. To talk a little about this camera, the original wiring was designed by Grimm. Grimm is an Ukrainian astronomer and he did retro-engineering on several sensors and created cameras on this basis. You can find all the information on the AstroCaf website and the astroccd.org. Maybe you remember I made two Cam10 cameras for auto-guiding and planetary imaging. You can see the link to this video above. And for French guide there is the WebAstro website and the French version of this video. So I put here the first picture I made with this camera, cooled to -5°C. There is here only 14 3-minute shots auto-guided. The auto-guiding was made here with the Cam10, so there is a 100% DIY camera system with an OAG and the mount was an NEQ5. So we're gonna keep this picture as a wallpaper. This is M101 and we'll show you all the steps that led to the homemade manufacture of this camera. The first thing to do was to choose a diagram because there are several diagrams, and the other resulting from the modification of that of Grimm because there is diagrams which were improved. So here you can see the original diagram by Grimm, and you're gonna see that there were some little stuff that were improved by another user. For example, this one from Lordzop. This is a good guy from the French forum WebAstro. I found this one particularly interesting because he replaced some weak components by stronger ones. He changed the way to power feed this camera. On Grimm's design, all the logic parts of this camera were fed by the 12 volts input. And on this Lordzop design, all the voltages are generated by the power coming from the USB port. And it is very interesting to do that because Grimm has mentioned the problem with the 12 volt because it feeds also the Peltier module, which consumes a lot of current. So when the Peltier module is active and draw current through the 12 volt lines, there is issues on the logic part of the camera. So it's useful to use the 12 volt only for the cooling and have a separate feed from the USB port for all the logic parts of the camera. So the first issue I faced off was there was mistake on the Grimm's diagram and there was also mistake on the Lordzop one. So I had to compare both diagrams to correct all the errors there was on both to finally design my own diagram without errors. I also had to modify several things because of my design. For example, the 3 volts is made from the 6 and no more from the 5. I've completely changed the cooling part, we're gonna see that later. So here is the final diagram that emerged from all these investigations. Next, I made a 4-layer PCB. Why a 4-layer after all the Cam87 was made of 2 layers PCB? I wanted to have all chances on my side to improve the signal to noise. The electronic part was already well improved by Lordzop. The only thing that missed was a 4-layer PCB to make it less sensitive to the electromagnetic perturbation we can have to improve the camera performance. So in this first layer of this PCB here in red, We have a logic part and a power part. I've pushed as far as possible the power part on the board to avoid these components to make electromagnetic perturbations, and as well as these components heat up, they produce infrared radiations. To prevent these infrared photons from being captured by the sensor, they must be placed as far away as possible because they can generate additional noise. So here this is the back side in blue with all the logic components. I've placed the analog converter as close as possible from the sensor, so the trace is short and it minimizes the perturbations. For the same thing, to minimize the perturbations, I've placed all these components on the opposite side from the sensor. And we have two inner layers. The first one here in green is a track layer that you can see here. And the other layer is a ground layer with a full copper plane to have a return to the ground as short as possible. So this was the cam board. So we're gonna see now the power board. So we have here the power board, which is also a 4-layer board. This board generates all the voltages for the logic part of the camera, and it also has the circuit for the calling part. All the tracks are sized for the amperes that goes through. You can go up to 2 or 3 amperes. I've also changed the MOSFET by another one, which is a great MOSFET. This is a AO4410. This is a teeny MOSFET that can go up to 18 amperes, and you don't heat at all in this range of the amp of this camera. So doing the best to minimize the electromagnetic interferences. So there is a lot of little things, maybe you saw that. So for example, I've put a lot of vias near the sensor pin. These grounded vias are useful to intercept the unwanted waves, to prevent them to reach the sensor pins. These are also useful to improve heat dissipation because the sensor is cool and the board is warm. The design of this camera is made to be a shield for the electromagnetic unwanted waves. As I said in the beginning of this video, this camera is inside an aluminum box. Also, the aluminum box is a kind of Faraday cage. It can block all the EM that's coming from the outside. Some have made entirely 3D printed cases, but since some components are sensitive to EM radiation, this seems to be less suitable. So outside this camera there is a little 3D printed case, and inside this case there is a power board, and on this board there is all components that can make unwanted waves. For example, all the cooling part, the self, the components like the MC34063, which are used to generate the +15 and the -8 because these components generate 100 kHz frequencies. So here we can put all the chances on our side to improve, optimize, so that this camera can generate the best signal to noise. I've seen on many forums that for people who want to make a camera, the most difficult thing was not the soldering or the electronic part, but the machining, the assembly of the box. So I make the thing here easier as possible, so you can make the machining on the easier way. Next is the design part. Here is the part that I designed. Here is the cold finger. This piece is meant to be machining in aluminum. GLC PCB made it for me. It's doing this job very well. They can make this piece for less than $50. So this piece have a round part on the top, where the Peltier module will sit, with the heatsink above. The little hole here was for grounding the cold finger, but finally I don't use it. The other hole on the side here is to place the temperature probe, which is in TO92 format, and below there is grooves for 2 O-rings. So this cold finger was going through the aluminum box. The 2 O-rings will make a thin layer of air between this cooled part and the aluminum box. So this cold finger will be pressed against the aluminum box with a 3D printed piece that you can see here, which includes several holes designed to receive washers. You have here the path for the 2 Peltier cables. And if we take a look below, You can see here the cold finger will be placed in this circle right here, and the screws will pass through this piece, through these holes, to be fixed in spacers, and the spacers will be fixed and glued on the aluminum box. Here you have 4 nuts to glue to fix the heatsink, which will go behind here, and this hole was to pass the ground wire for the cold finger that I don't use. I've also provided a support for the power supply board, which is here. Here you have the 2 passages for the Peltier wires. On the top side you can see 3 holes for the screws with the same spacer system, and below you have passages for nuts, which will be used to fix the lid. Here you have the 2 passages for the 12 volts input and the USB. Then you have the lid for this part. So the cover will sit on top of the support for the power supply board. And you can see here a little passage for the fan cables, and here a screw to fix an ESP32 board here. I will explain later why I did this choice. And these 4 little holes here I used to fix the lid on the power supply board holder. Then we're gonna see the sensor mask. This mask will be glued on the aluminum box, and here this piece is used to fix the fan on the heatsink. It will be clipped on the heatsink. This stuff is a drill guide. It will be used to make a mark on the aluminum box on the right place for the drilling. You have to put it on the cold finger holder. There is here another piece which will be used to insulate the cold finger from the warm environment in the box. Here we have a very important piece used only for the mounting. This piece is used to place correctly the 3D printed piece that maintain the cold finger right here. The goal is to use this wedge and the cold finger holder to mark the aluminum box in order to drill the holes in the exactly right place. And we're going to see that there is no room of maneuver because I've chosen the smallest box as possible in order to minimize the air volume in the box, in order to have the humidity level as low as possible. And we're going to see that this is possible to reach and maintain 0% humidity in this camera. So here we have a view of the assembly. Here we have the cold finger with the 2 grooves for the O-rings. We can imagine the aluminum lid that come here and the cold finger that passing through, the electronic board that come here, and the sensor which will be here on this side of the cold finger, a hole on this side for the sensor probe, and the power board that's passing through the aluminum lid here using a DB9 connector. This is for this reason that I changed the wiring diagram, because I had only 9 ways for this connector, and this is for this reason I've produced the 3.6 volt with the 6 volt and the 6 volt with the 15 volts. So here we have the holder for the power board, and if we take a look above, we have the lid with the little passage for the fan wires, and it will be plugged right here on the power board. And we have a little hole here for the USB-C connector from the ESP32 board. It is used to program the PID inside this board. So that's it for the mechanical part. As I said before, I used an ESP32 to control the sensor cooling in this camera. So why I did that? The first reason was the original cooling managed by the logic of the camera was causing issues for several users. Some users have experienced issues in reading sensor temperatures. This cooling generates some noise, and the cooling must stop during the sensor reading phases, so as not to disturb the image too much. I wanted a more robust system so that the sensor temperature would remain truly constant throughout all the acquisition phases. The idea that made me to decide to go down this way, and I think it's the best way, was when I saw the image made by an Italian stargazer named Carlo Caliguri. He produced some stunning image with his Cam87. Then it should be remembered that this camera sensor was used in commercial cameras sold until a few years ago, which cost, no pun intended, a astronomical sum of money. Despite the age of this sensor, it is still capable of generating very satisfying images, and its format is very pleasant to use for large targets. So I got in touch with Carlo, who is a very nice guy by the way, and who gave me a lot of information. Big thanks to him. He explained how he did that. He used an ESP32 with a home automation system. I wanted to do something a bit similar but simpler to use, so I used an ESP32 data program to read the temperature of the sensor probe and the temperature and humidity of a STM32 sensor in the box. These informations are used to calculate the dew point. With all this, I made a web interface. There is a web server on this ESP32, and you can connect with your phone to display temperature, a graph to see if the temperatures are stable, the dew point calculation with an alert system that can be triggered when the sensor temperature falls below the dew point and icing is possible. There is also an option of switching to night mode. The connection is made by direct Wi-Fi. You can connect on the Cam87 Wi-Fi signal, and then you can have access to the temperature, the dew point calculation, the graph to see if the temperature is stable, the night mode, and there is a PID from an existing library that works very well, and it gives very stable temperatures during all the acquisition process despite of the sensor heating. So before you see any construction footage, I've decided to show you straight away how the setup works so you can see exactly where we're going. So here there is the lid with a rectangular hole for the cold finger passage, the 4 spacers to fix the board and the DB9 connector, and the spacers to attach the various 3D printed parts. Here we have the box with a circle hole and a system of rings and a seal to fix the window. The seal is made of 2 mm thick silicone. Here we have the aluminum cold finger with 2 grooves for the O-rings, a hole for the temperature probe. On the other side you have the useless hole for eventually grounding this piece, but it's useless. On the top you will have the Peltier module, the 2 O-rings for this cold finger, 37 and 42 by 1.5. So you grease the 2 O-rings and place the cold finger like that. Beware to have the sensor probe on the right side. So here you'll find the part that will hold the cold finger in place. Don't forget to glue the nuts to fix the heatsink. So this piece is placed like that. Then you tighten the screw just enough to make the stuff gas tight. Then we have the 3D printed piece which is used to fix the power board. You place it like that. So here we have the power board with the Peltier module, the DB9 connector. So we place it like that, and the Peltier module will be tightened between the cold finger and the heatsink with thermal grease. Then we have the heatsink that will come here over the Peltier module. Here we have the lid of the power supply port with the ESP32, which is fixed with the screw, and it's powered and communicate with this connector, which will be plugged right here. Then the power board lid will be placed like that, with back the heatsink that will come here. Then we will have the fan that will be over the heatsink. And you have the fan connector here. It will be plugged into the power board on this little connector right here. To fix the fan to the heatsink, we'll use this part, which will be positioned like this. It is inserted into the heatsink to lock it in place. If necessary, screws can be inserted between two fins to secure this part. Then the heatsink is fixed to the cold finger holder with 4mm bolts. So here we have the cover with the cold finger and the DB9 gas tight plug, and here is the temperature sensor, which will be placed in the hole of the cold finger with thermal paste. Next we have a piece to insulate the cold finger, creating a thin layer of air between it and the warm environment of the camera, because the best insulator is air. After that, the camera board is placed on top with the sensor in contact with the cold finger using thermal paste, and we have the DB9 connector, which will be plugged into this large wide angle connector. On top of this we'll have the mask, which is designed to avoid stray infrared reflection coming from inside the case or stray reflection coming from the outside. It masks everything around the sensor, and then you have the case with the window, which will be positioned like this on top. So I kept the protective cover on the sensor until the end to avoid stretching it. Then for the window I used the 44.17 by 1.78 gasket, which fits exactly into this M48 thread against a small stop here. And on top of that I put the disassembled 2-inch UV-IR filtered glass and finally an M48 to M42 ring that will press the filter against the gasket to ensure a gas tight seal. The manufacturing starts with the electronics, so here are the two PCBs for this Cam87. So on this power supply board we'll have a few through soldering joint for the USB power supply DB9 socket, fan ESP socket, and the rest will be SMD soldering. So if you'd like more information about SMD soldering, here's a link to the Cam10 construction video above. So here is the camera board with all the logic components on the back, and on the other side a few components for the power supply, the connector for the power supply board, and a large APS-C sensor. Concerning the sensor, I bought this part on AliExpress, which cost me about 20 bucks. It's a replacement part for the Nikon D7T, which is equipped with this famous Sony ICX453 AQ-CCD sensor. So now we'll have to unsolder it. One thing that surprised me a little when I received this part was that there are holographic labels with the date of manufacture at August 2024. Knowing that this device is no longer sold, it's very strange that they're still making parts unless they are fake labels. In any case, this sensor works well, and once the camera is mounted we'll have seen it. So the first thing to do is to desolder the sensor, which was quite easy, because the alloy used for soldering seems to melt at very low temperatures. Another funny thing about this spare part of dubious origin is that I've removed a piece of tape, and underneath there's a chip stamped Nikon that looks genuine. Once the sensor has been desoldered, we have this, and most of the work remains to be done. Here we see the sensor number and 3 holes for filling with resin. So the sensor is glued to the resin on the aluminum plate. This resin is a little soft and can be removed by stretching the holes. Then we place a few drops of a solvent called DMSO, which will dissolve the resin. So we put some in the 3 holes and in the middle, and by capillary action it will get between the sensor and the aluminum plate, and then we turn it upside down to prevent it from leaking into the sensor protection. So I left it like that for 3 or 4 hours, and then I reverbed it out with a screwdriver on the side. Don't hesitate to use a little force, as it often comes right off. So here the sensor is protected by a plate which is an infrared filter. I'm going to keep it to protect the sensor, and underneath you can see that there's a lot of resin that needs cleaning. The sensor reference is clearly visible below. We'll now move on to cleaning. So here's the sensor after a good cleaning with a perfectly smooth surface for good contact with the cold finger. I can almost see my reflection in it. I used a little abrasive to remove the resin. Then I cut off the end of the legs that had a bit of alloy on them, so that it fit better into the holes in the PCB. So here's the sensor in the PCB. Here I put it on the wrong side. Fortunately, I hadn't done the soldering. At first it's quite complicated to fit it in. You have to align the pins and remove any remaining solder. So I started by making the temperature sensor. It has to be soldered to the connector like this. I'll leave it to you to mark the position of the wires on each pins. Then I soldered all the components and checked them with this little tester, and I did well because I found a faulty component. If I'd missed it, I could have looked for a long time. After soldering all the components, I cleaned up the board with isopropyl to remove all trace of flux. Then at this stage I was missing a DB9 socket to make the connection properly, so I connected the two boards with wires and toothpicks. Then I moved on to programming the STM32. So to program the STM32, I'll leave you to find the positions of the wires, reset clock 3V 3 SWDIO and the ground. Then we'll use this key from ST Microelectronics that you can find just about anywhere on Amazon or AliExpress, which will be used to program the chip. Then we'll connect the SWDIO, SWD clock and ground wires, and only those. Then plug in the USB key and launch the chip flashing utility. And we'll flash this chip after the driver's installation. So at this stage we need to install the driver. So we go to the FTDI website and type FT2232HL. We'll find the drivers for our chip here, so we click on them and then on drivers. Then we go to VCP drivers and download the latest version. We take the top one, which is complete with all versions of Windows. So you have to be careful with drivers because for a few years now FTDI has breaking copies. So if your chip comes from AliExpress, I suggest you install the 2.8 driver included in the package and not the latest version, because you will install the driver and it will work, and when you want to plug the camera in again, it won't work. Of course, there is no problem if you bought your chip from an official FTDI dealer. So I unzipped the drivers, then went to the device manager, clicked on USB serial converter A, and went to find the driver to update it. Once you've done the update, go back to USB converter A and go to the Advanced tab, making sure this box is unchecked. And do the same with USB serial converter B, unchecking the box. So once you've installed the drivers and logon, we'll use the mprog utility to program the FT2232 EEPROM. Go to Device, Scan, and you'll see that you have a device to program. So we go to Tool, Read. We see that everything inside is empty, so we go and find the file to be programmed. File, Open, and we find our Cam87.ept. Then we go to Device, Program, and Tools, Read, and we see that our camera has been programmed because we see the Cam87 info appearing in the memory. Now that we've done that, we'll launch the viewer to connect the camera to program the STM32 chip. This chip will be programmed using the USB key I showed you earlier. We'll launch the STM32 ST-Link utility and go to Target, Connect, and you'll see that the EEPROM is empty. We'll now program the file, open, and look for the Cam87.bin file. We see the information inside the file which appear in yellow. Go to Target, Program, Start, and off you go. Once the chip has been programmed, everything appears in white. At the bottom, you can see that the operations were successful. You can now close the utility and launch the viewer to see if the connection and image acquisition are working. It has to be said that for the moment there is no sensor. So we set these parameters and make get image. You should get a sort of histogram like done on the screen and some noise which comes from the electronics. So before soldering the sensor, I checked all the voltages, the +15, the -8, and the return on the camera board, the +15, the 6 volt, the 3 volt 3, and the 1 volt 8. So is the power supply board with the two shielded coil shaft cell for the +15 and the -8 circuit on either side. At the bottom you have the coil and the aluminum polymer kappa for the Peltier circuit. 12 volt and USB power socket, connectors for the fan and the ESP32. On the other side you have the two MC34063 chips that will manage the +15 and the -8 volts. The voltage converter on the left is the one that will make 5 volt from 12 to power the ESP. At the top, this is the famous A04410 MOSFET for powering the Peltier. And in the center, there is the DB9 connector with ground for the camera and ground for the cooling unit, which is completely independent. The temperature and DHT signals the 5 volt generated from 12 to power the ESP, but also the DHT and the temperature sensor, the +15, the -8, and data plus data minus of the USB. Here you have the PCB camera with the sensor slot, the small white connector at top right for the temperature sensor, the large connector for the power supply board, the small connector at bottom for programming the STM32 chip. On the other side are the sensor drivers, top right and bottom left. The analog converter is at top right. In the middle it's the FT2232 chip, bottom right is the STM32 chip, and the little 8-pin EEPROM on the left. And here at the bottom are the DHT22 and the LDOs, which will make 6 volts from 15 and 3 volts 3 from 6. You may have noticed a correction on this PCB. It was a mistake on my part. I had forgotten a single ground on the whole circuit and an error on the part of Easy EDA, which had a footprint error for this LDO component used to make 1 voltage from 3 volt 3. So don't worry if you're looking at this camera, I've corrected the PCB. So now that I've got the DB9 connector I was missing on the power supply board, I'll be able to connect this gas tight connector. I've protected the joint with tape to avoid damaging it. I'll let you spot the colors. Then I'll solder the sensor. I'm going to solder it directly with the header to optimize the connection. I've put 2 layers of paper to prevent the sensor from coming into contact with the PCB since the sensor is cooled. I'm showing you some adjustment I had to make to the 3D printed part, which I did with the Dremel. You'll probably have to do it too. There are some minor dimensional error on this 3D printed part. So here on the power card support, I remove a little material from the top. On the lid, I've removed a little thickness here because I hadn't noticed that the PCB was flush at the back. So the power supply board is placed here. It's well plated. I had planned all the thinnest components at the back on the board. And the lid come on top like this. Here's general view with the USB and 12 volt connectors on the front and the DB9 connector underneath, which will send all informations and voltages to the aluminum case. At the back, the fan socket with the wire fit through. The various fixings don't forgetting the nuts. A small hole at the top to see when the camera is cooling down, if the PID is on full blast, or if it's regulating. You'll know if there's room to lower the temperature. For the cold finger, scraped inside the probe hole to remove the excess of aluminum oxide, then blew it out with the compressor. I also filled the edge of the component so it will fit because the hole isn't exactly the same size as the TO92. You just have to sand the corner like this to make it fit. Don't forget to put thermal paste in the hole before inserting the probe into the cold finger. So now I'm gonna place the shim for the tape hole to fix the spacer in the cover. I put an aluminum shim on each side and a few layers of paper because this case is painted and a little thicker than the drawings. The shim was floating a little, so I put this piece of paper in place. Then we secure everything with a clamp so it doesn't move. Be careful, you have to place the shim right at the edge, looking at the vertically because the edge of the box is not orthogonal. On the side, you must measure in relation to the lid and not in relation to the edge of the box, which is not perpendicular. I marked the cover with my drill guide and a needle. Then I mark a little more and check carefully before drilling. Next we drill at 2.5 mm and tap at 3 mm. This is truly the most crucial step. You really have to take your time. All it takes is for one spacer to be slightly offset inward and the cold finger won't be able to get in. Here I mark the lid with the power PCB. So here you have the cover with the spacers installed, the part that will seal the cold finger. I had to tweak it a bit. I had a spacer that was a little offset locally, it was facing outward. And here the part for the power supply board. So here you can see that it fits right up to the edge. On the underside you can see that there is an inscription with the case references, so you shouldn't bother to sealing the cold finger from here. That's why I chose to do it from the top. Then for the hole for the cold finger passage I made a small cardboard template to the dimensions. Then I placed it in a holder, then we mark the corner, we drill a little file. And at the same time I started to remove this part in the case because it will hit the PCB. So this is a little long to do. The aluminum alloy that makes up this case is quite easy to work. It's a little brittle and the longest part is to remove these parts in the case. So once it's finished, a small assembly test with here the hole for the DB9 and the hole for the cold finger passage. So the cold finger in position, the holder on top, the power supply board holder, the power supply board, and there it is all assembled. A small close-up profile view. Regarding the DB9 connector, I fill it almost to the edge of the seal like this to make it easier to pass through, and I shifted it here. There is a little less space here than here, so I'm gonna explain why. If we turn the cover, we can see that this part will hinder the installation of the connector. That's why you really have to be careful when using the shim and place it well, because if it's shifted 0.5 mm downward you won't be able to place the connector. So here are some pictures of the assembly with the power board connector. After that I've placed a blank PCB here to mark the 4 mounting holes for the camera PCB, which will be drilled in 2.5 mm and tapped in 3 mm in the lid. So here are the 4 15 mm spacers screwed into the lid. Then I tackle the porthole part. We put a shim and make a mark 41 mm from the edge. We can clearly see here that the case is not orthogonal. We must be careful about that. We must not measure in relation to the edge of the lid. We draw a nice circle with the diameter of the M52 M48 ring, which will be placed behind, and we make tangent holes. A little work to join the holes. Finally we finish with a file to have a nice round hole. Here's where the case with the parts to be removed. Then I cut the silicone gasket so that it fits into the FT22 M48 ring that I have, as you have seen, filled on the side. It's a 60 by 2 mm gasket. Then I sanded the paint to have a smooth surface to maximize the seal. I did the same behind for the DB9 connector, and I did the same before mounting the window. Like this, with the M52 M48 ring in the back, we put the gasket and we screw the 15 mm M48 ring fully. Then I soldered the peltier. Here we have the 12701, which consumes 1 ampere and produces a delta of 20. I also tested a 19003, which consumes twice as much with a delta of 25 degrees. It's up to you to see which one you choose. Here we have the ESP32 installed, let you locate the position of the wires to be soldered on this board. So we have the ground of 5 volts, and we have 3 wires for the data transfer, so here the 5-pin connector. For the fixing, I put a piece of plastic with a washer and a nut. On the other side we have a hexagonal flat head screw. So on the side we have the USB port to program the PID. Here is the hole to display the cooling status LED. So at this point I dusted everything off and kept the part in plastic bags so as not to contaminate with dust. Then I glued the spacer to ensure gas tightness. I used polyurethane glue. I put some on the male and female thread and tightened the spacer well. I also put glue here that I let dry to create a small elastic layer before placing the DB9 socket. So here are the spacer brushed with glue, then all that left is to screw them in. Then I did the same with the nuts to tighten the spacer well, glue in the nuts and on the threads and tighten well so that it can no longer move. I glued the 4 nuts in the holder to fix the heatsink. So here the PCB fixed on the lid with screw equipped with springs. Here is for the DHT22. I removed the bulky cover and put some Kapton to prevent short circuit. Then I assembled everything to see if everything fit properly, and it did. The 2 O-rings previously greased with tap grease placed on the cold finger. Then I assembled everything and installed the screws. So I did not put the wire to ground the cold finger. Apparently it has no effect. This may have been necessary on camera that had a common ground between the camera and the cooling, but this is clearly not the case here. So here are the various nuts glued into the holder for the power supply board. I installed the temperature sensor with thermal paste grizzly cryonote, which is known among extreme cookers who use liquid nitrogen, so for the cold no problem. I glued the small insulator, so here the whole assembled. Then the sensor mask. I had to file a little bit at this place because the temperature sensor socket was a bit annoying, and I glued it. A little Kapton on the screw to avoid short circuit. Then I installed the power supply board on the lid and fixed it. With thermal paste under the peltier, this time silicone paste that does not dry, so I definitely fixed the cord, connected the power supply board, and I put thermal paste between the cold finger and the sensor. I put the protection back on the sensor and put some glue on the power plug wires so they will not come loose. After this I moved on to the assembly of the window with the gasket that I placed on the stop. Then I installed the UV-IR filter glass that we saw at the beginning of the video, and I screwed the M48-M42 ring so we avoid sticking our finger on it. We can wear gloves and we be careful of dust. I use this tool to tighten the ring, very practical tool for disassembling lenses. So here is this window. I put a cap to prevent dust from entering. Then I made a paper reservoir for the silica gel of 26 by 55 by 10 millimeters. I recovered some silica gel that we find with electronic components. I opened it and filled the small reservoir. So before placing these small balls in the reservoir, it is absolutely necessary to regenerate them. If you do not do this, you will not be able to reach a low humidity level in your camera. So to regenerate it, I advise you to put it in a small plate and put it in the microwave for 5 times for 30 seconds to 1 minute. Immediately after filling your reservoir, close it and immediately close the camera after having thoroughly dusted the inside with the compressor. Once the camera was closed, I put a thermal paste on the peltier. There is thermal grizzly cryonet for the other place between the cold finger and the camera, and between the cold finger and the peltier I put silicone which does not dry. In this part the cryonet could dry out and turn into glue. I sanded the heatsink to obtain a perfectly flat and smooth surface. I used progressively finer sandpaper from 600 to 2000 grit, then a little polish. Then I fixed the heatsink with the screws and springs. So everything is assembled. All that left is to put on the powerboard cover and the camera will be ready to use. Then I attach the fan to the 3D printed part, which will attach to the heatsink like this with the plug connected. Now all that left is to put on the powerboard cover, so the camera is finished. For the assembly I dusted the inside, especially the sensor on the window. Now we're going to program the PID in the ESP32. To do this we retrieve the Arduino code shown here, open the .ino file, go now to Tools, Manage Libraries, or simply click on this icon. I will install all the necessary libraries. You'll find the procedure and the name of all the libraries in a provided package, but we'll see now how to do it together here. So you're going to type Paul Stoffregen and install the one-wire library, which is already installed here. Then you use Miles Burton to install the Dallas temperature library, DHT sensor library to install the Adafruit library here, then use the Adafruit unified sensor, and finally the PID by Brett Borgar. Next you need to install the plugin to create the web server on the ESP32. You need to copy the Arduino little fs upload.vsex file. This will create a disk on the ESP32 board where you can store a web page and scripts. Copy the file and paste it into the following path: C, user, your name, .arduino IDE, and plugin. Next you need to unzip these two libraries here and place them in the following folder, along with the Arduino libraries in C, users, your name, OneDrive, documents, Arduino libraries. Next, before starting the procedure to flash the ESP board, make sure you have the data folder next to your .ino file containing the web page to be installed on the board. Here you have the HTML file containing the interface and script of communication with the ESP board and displaying the graph. Now that we've done this, we can move to programming the ESP32. We connect the board with a USB-C cable, then in the Arduino IDE, go to Select Board, select Other Board and Port, and type vroom, W-R-O-O-M. We choose this board and the recognized COM port. We click OK. Then we click Upload and wait while it compiles and uploads to the board. Once the upload is complete, we'll send the files contained in the data folder to the disk created on the board's flash memory by LittleFS. To launch LittleFS, we press simultaneously Ctrl, Shift and P. We type LittleFS and launch the plugin that appears in the list. We wait for the process to complete. And that's it. It's done. The PID is ready to use. I greased the main gasket and at the DB9 connector. Only the window didn't grease. The app showed that the humidity level dropped quite quickly, and the next day it was at 0%. 1 month later it is still at 0%. The camera seemed to be gas tight. So here this video is finished. I hope you liked it and that will make you want to make it. A big thanks to Dream, the designer of the circuit of this camera. A big thanks also to Carlo, who gave me some good information which allowed me to choose the way to make this camera. And I leave you with this beautiful image of this APS-C sensor on this Cam87 Astro 18 edition.